Lesson 2, free body diagrams. I'm going to teach you today what a free body diagram is, which is sort of the Swiss Army knife of forces. But we're going to start off with some review. Recall Newton's second law, which was F equals ma. What is some stuff that we can do just with that already? Well, example 1 says this. A spacecraft has a mass of 3.5 times 10 to the 4th kilograms. Its engines can exert a thrust force of 7.25 times 10 to the 4th newtons. Cool. Mateo, what does part A want me to find? Thank you. I was going that. You know what? Again, you guys are in line. So, yeah, sure. You, Mateo, back there. I'm in. What do you got? So I'm going to do my A equals question mark. Now, up until now, Mateo, when I've said find the acceleration, you've thought to yourself, oh, I'm looking for a VI and a VF and a T and a D. Look at what they gave me. Do you see a VI or a VF or a T or a D or anything like that? So now we're going to add yet another way to find acceleration. And it's really just kind of a checklist where you run through what they've given you. See this equation here, kiddo? Get the A by itself. What's the M doing to the A? Adding, subtracting, multiplying? How will I move the M over? You know what? Let's write it down. Can you give me a new equation for acceleration? Yep. Acceleration is also the force divided by the mass. In fact, nerd trivia, this is how Sir Isaac Newton actually gave his equation. He was more interested in acceleration than in force. But, okay. Really quickly, Mateo, did they give me in the question a force? Yeah, newtons, you see it? Did they give me a mass? Kilogram? Oh, well then, hey, plug and chug. The acceleration is going to be F divided by M. It's going to be 7.25 times 10 to the 4th newtons divided by 3.25 times 10 to the 4th meters per second. Connor right now is saying, hey, Mr. Dewick, is there a 10 to the 4th on the top? There is. Is there a 10 to the 4th on the bottom? There is. Now, that's a fluke because I was just making up numbers, and I guess I happened to make up numbers. But since it's there, yeah, they'll cancel. We can. So you could go 7.25 scientific notation button 4 divided by 3.25 scientific notation button 4. Or you could go 7.25 divided by 3.25. Regardless, I'll do the second one because I'm naturally lazy. I get 2.230. You know what? 2.23. Mateo, units, acceleration. Yep. Who remembers how big is 1 g of acceleration? This is about a quarter of a g. Oh, sure. How many of you have been at Playland, the musical swings that go in a circle, the ones that you sit in with the bar that goes across, you hang from the chains? That I've gone on there. That's about 2 meters per second squared. It's not in other words, you've experienced it. It's not very big. You'd feel it a little bit. Yay. Okay. Mateo, let's keep going. What does B want me to find? Okay. Well, as soon as I write that, now I'm starting to go back. Remember before Christmas, I'm thinking maybe a VI or a D or a T, or I was going to say or an acceleration. But what did I find in part A? The acceleration. You know what? I bet you I can use that. Let's go look at this question. What's that 240 in part B? How do you know for a fact that it's time? Hey, did your teacher tell you it was worth memorizing what units go with what? He should have. What's that 5.6 times 10 to the 3rd? VI. And I can drop the acceleration down from part A. Hey, Mateo, is there an equation on my formula sheet that has those things in it? And I think it even has the VF by itself already, yes? So pause for 1 second. Folks, as far as I'm concerned, all of those equations are fair game in this unit because there's such an overlap between accelerations. Okay? In fact, eventually, remember the RCMP speeder question where I had the cell phone time how long the skids lasted, and that way we could prove that he was speeding. That was such a fake question because cell phones wouldn't time how long the skids lasted. But with forces, we'll actually be able to get it from how long the skids are, and we can actually work back. Anyways, which equation there, Matteo? It's going to be 5.6 times 10 to the third plus 2. I'm going to write 2.23, but I'm going to use my answer button. Was I hearing like headphones or something there weird? No? Okay. Or it could have been the weird fan here in the projector in my ear. 5.6 times 10 to the third plus, answer button times 240. By the way, 240 seconds, what is that, 6 minutes? No, 4 minutes. 4 minutes, right? Okay. So we turn the engines on for 4 minutes and then we shut them off. How fast will we be going after 4 minutes? That fast. Okay. 6135 point, that 3 there is going to become stay a 3 or become a 4? I'm going to go 6.14 times 10 to the 1, 2, 3. Meters per second because it's a velocity. Part C. Oh. Matteo, what's part C asking me to find? Okay. Matteo, did I list all my data in the previous line? I'm not gonna, you can drop it all down, write down T equals, and you know. Hey, Matteo, what equation can I use here? Please make sure it's got a D in it. That'll work. I think there's another one with less brackets that'll also work. No. Karn, you are correct, sir. By the way, all of those are right. I wouldn't use the VF squared, VI squared 2AD because I'd have to get the D by itself, and I'm lazy. In none of these can I avoid using something that I calculated. The first one that you mentioned, I'd be using VF, which I found in part B. So I went with this one because if I'm going to use something that I calculated, I think I got the A right, and it's less brackets, it's more plug and chug, and the D is ready by itself. Okay, so all of yours were the right answer. One of them is the laziest answer. I think this one. Because VI, they told me, was 5.6 times 10 to the third. T is 240 seconds plus a half. I'll use 2.23 for A. 240 squared. Okay, in 4 minutes, how much distance have we got? It's going to be a fair bit because I got these ships going pretty fast. You get that? You know, I'll go to 3 sig figs. 1 sig fig, 2 sig figs. There's the 3rd sig fig. Is it going to stay a 0 or become a 1? Become a 1? So it's going to be 1.41 times 10 to the 1, 2, 3, 4, 5, 6. Units, meters. You know what, Mr. Dewick? Let's be clever. Because you can. Yay. Meters. D. All right. What will the velocity of the spacecraft be after 480 seconds? Or after 600 seconds? Or after 1,000 seconds? You don't need a calculator for this. You don't need a calculator for this. What's the answer? Do me a favor. Go back to part B and underline before turning off the engine. What was that? What was that? No, not constant acceleration. If you turn off the engine, constant speed, no acceleration. So, Michael, it'd be what? 6.14. Now, Newton's first kicks in. You're going to keep going in a straight line at a steady speed because in outer space there's no force acting on you, Carmen. This is again why we hold, one of the reasons we hold Sir Isaac Newton in such esteem. Back in 1670, 1680, he was imagining outer space at a time when there weren't airplanes or even hot air balloons. That, Jared, is in theory kind of all review in that I haven't showed you anything new. I just wanted to show you already where we can use Newton's laws. But now, let's get to the meat and potatoes. Free body diagrams. Or an FBD for short. A free body diagram is a picture. And what you do is you represent the object that you're analyzing with a little dot. And any forces that are acting on the object are drawn as arrows. Nick, roughly to scale. And by roughly to scale, I mean if you know force A is bigger than force B, make force A a longer arrow. If you know force A is twice as big as force B, make it about twice as long. Roughly to scale. Newton's laws are used then to figure out any other missing forces that are acting on the object. You ready, Karin? Because I'm coming to you. Okay? We're going to do example 2 together. It says this: free body diagrams for force situations are shown below. The net force is known, but we're missing some. Karin, you and I are going to do the first one together. See it? What does it say that the net force on the object is? 0 newtons. That means apparently the overall force is 0 newtons. How many in the picture, how many newtons are pointing down? How many newtons are pointing down?
200.
If the net force is 0, how many newtons must be pointing up? That's the question.
200.
Yes. This is the usefulness of Newton's first law. I know if my net force is 0, everything has to be balanced. Force B has to be 200 newtons up. Based on that, can you figure out how big force A has to be? If my net force is 0, how big must force A be? 50 newtons left. Is that okay, Jilin? Because I'm coming to you for the next one. You ready? This one here. What's the net force, magnitude, and direction? 900 newtons, which way? Okay, I have 200 newtons down. How big must C be so that I end up with 900 newtons up? Not loud and proud, you're right. Say it again. Like exactly 1100. This is the usefulness of a free body diagram. If you get some of your forces, you can reason your way tie to what the other ones have to be, using Newton's laws. Adam, what's the net force in this diagram here? Direction? Okay, let's do the verticals first. What's the net force vertically? Okay, so what must, because they didn't mention it, so we'll assume 0. What must E be?
300.
What must D be?
20.
And do you see, Renzo, how that gives us 60 newtons left as our net force? What do I mean by net force? If you add up all the forces, keeping in mind, Cassidy, the directions, and replace it with one force, that's the net force. Mateo, front row. What's the net force in this question? So how big does G have to be if you want 30 newtons to the right? Yep. What's the vertical net force? Well, what will we assume the vertical net force is? 0. So how big is F compared to H? Have to be the same. You know what? I don't even care how big they are. I do know that they are the... In fact, let's go like this. That equals H, and that equals F. Now, you might say, Mr. Dewick, doesn't F actually equal negative H? You know what? I took care of the negatives with the arrows. That's the directional component. So in a free body diagram, Liam, what we do is we replace the mass with a dot. I didn't here. I actually kept the mass as a square just so you could kind of see things a bit better. And then we use Newton's laws to figure out what's going on. A book is at rest on a tabletop. A free body diagram for this situation looks like, there's the book. Represent it with a dot. What are the forces acting on the book? Get the obvious one. Now, the obvious one is the force that's holding all of you onto the earth. Gravity. I call that Fg, a capital F and a lowercase g for gravity. You know what? What we're really talking about is all of your binders. See your binders? Okay, sitting on the tabletop. What are the forces acting on your binders? Get the obvious one, gravity. Are your binders sinking into the table like quicksand? No. Are they flying into the air like Superman? No. I'm going to ask you the same question. I want the same answer. I'm just going to phrase it differently. Are they accelerating? So is there any net force acting on them? So as a number, what's the net force acting on them? 0. 0. That diagram does not have a net force of 0. There has to be a force pointing up. Am I going to draw that arrow bigger, smaller, or the same size as gravity? Same size. Net force of 0. So everybody draw an arrow. Make your arrow the same size, your up arrow the same size as your down arrow. What force is that? F table. Gravity pushes against the table pushes back against gravity because forces come in pairs. Is that okay, Gillian? We can go even more specific. Number 12 says, draw a free body diagram for the following masses. You know what? We've got two situations. Here, let's represent the mass with a dot. What are the forces acting on this book? Get the obvious, on this mass. Get the obvious one. Now, whenever I say that, and this is going to be Sage, my approach, whenever I start a free body diagram, you're going to hear me say, what are the forces acting? Get the obvious one. And the response is going to be, unless we're in outer space, gravity. And I'm doing that, Sage, for a reason. What I'm going to be doing today, Karn, I cannot give you one equation that works all the time. What I can give you is a method that will work all the time. So now we're going into a little unfamiliar territory. So part of my method is going to be do things in the order that I recommend, because I almost want you to develop like a chain of physics dominoes in your brain so that once you tip over the first domino, all the rest of them just fall into place. What are the forces acting on this mass? Get the obvious one, everybody? Gravity. That wasn't everybody. Get the obvious one, everybody? Gravity. Good. Is that okay, Tori? Now, look at the picture. Does it look like that mass is accelerating at all? No. So I'm going to ask you the same question. I'm just going to phrase it differently. Are there any unbalanced forces acting on this object at all? No. So what's the net force on this object? That diagram is impossible, because that's an unbalanced force. There must be a force, Tori, pointing which way? Up. Am I going to draw that upwards force bigger, smaller, or the same size as my gravity arrow? Eyeball it roughly. What force is that? Well, it's the rope, but we have a special name that we give the force in a rope. We call it tension. The force in a rope. Capital T. So far, so good, Tori? Let's look at the right-hand diagram. There's the mass. Tori, what are the forces acting on this mass? Get the obvious one. I totally agree. Look at the picture, though. Which way is this mass accelerating, Tori? I'm going to ask you the same question. I'm just going to phrase it differently. Which way is there an unbalanced force, Tori? I'm going to ask you the same question. I'm just going to phrase it differently. Which force must be a bigger force than gravity, Tori?
Upward.
I'm going to draw an arrow pointing up, longer than gravity. Is that okay, Ty? Has to be. I'll exaggerate it to make it really obvious. Tension. Tension. Turn the page. Quick, like a bunny. A couple of types of forces, and we're going to get into more types of forces next lesson, but one of the forces that you're most acquainted with is the force of gravity. You feel it on you all the time unless you're an astronaut and haven't told me. Well, no. You also don't feel gravity if you jump out of an airplane. I mentioned I jumped out of an airplane. You don't feel gravity for a split second when you jump off of the high dive into a swimming pool, or when you're on your trampoline while you're in the air. And we like that feeling of weightlessness, of gravity still acting on us, but we can't feel it. The force of gravity is calculated as follows. F equals what? F equals what times what? F equals what times what? F equals what times what? Just say, how about MA? F equals what?
MA.
F equals what?
MA.
So gravity is going to be m little g, because that's what we've used as our acceleration for gravity. In fact, from now on, Priya, I'm actually not going to write Fg anymore. I'm going to write mg. I'll even go straight to the equation. Half the time you'll notice I just replace it with the actual equation, mg. Where g is not negative anymore, we'll take care of that with our arrows, 9.8. Another word for the force of gravity is, begins with the letter W. No, now. Wait, no, now. Wait, no, now. It's a joke, son. Wait. Adrian, our mass doesn't change whether you're on the moon or on Mars or in outer space floating. You still have mass. It's your weight, the force of gravity acting on you. It's our weight that changes. Weight is a unit of force. It's measured in newtons, not kilograms. Example 3 says, find the weight of a 35 kilogram object A on the Earth and B on the Moon, where G is 1.6. They still have the same mass on the Moon, but they will have a different weight on the Moon. You know what? Let's draw a little line right here. Let's call this part A, call this part B. Julie, what does example 3 want me to find? Another word for that is force of gravity. So I'm going to go like this. Fg equals mg. Fg equals mg. But you know what? Since in B we're on a different planet or celestial body, I'm going to put a little moon subscript to remind myself. Cassidy, if you just see a lowercase g on its own, assume you're on the Earth. Okay? But otherwise, if you're not, point it out. Cassidy, what's my mass in this question? What's g on the Earth? Not negative. We'll take care of this unit. We'll take care of the negative in our free body diagram with arrows. Okay? What about on the moon? It's going to be 35 times Cassidy. According to this question, what's g on the moon? 1.6. Can I do this in my head? Sure I can. 35 times 9.8. That's going to be 35 times 10, which is 350. Take away 7. 343? Double check me. Yes? 343 what? Weight. It's a force. It's measured in newtons. You know what? I should be able to do this on my own too. Timesing by 1.6, that's the same as doubling 4 times 7, 14, 28, 56? Yeah, okay. Newtons. So mass, go ahead. Mass doesn't change, Jay. Your mass is the same anywhere in the universe because mass measures your inertia, your resistance to force. Your weight, however, will change. As a matter of fact, because the Earth bulges at the equator a little bit and is a little bit shrunken at the North Pole, you will have the same mass on the equator as you'd have on the North Pole, but you'll have a slightly smaller weight on the North Pole, on the equator than you do on the North Pole. Because on the North Pole, you look closer to the center of the Earth. On the equator, you're slightly further from the center of the Earth. It's measurable. Not with humans because our weight fluctuates so much, even just breathing and sweating and all that. But if you take a well-machined piece of metal, you could measure the difference, not in mass, that wouldn't change, in weight. Here it is, the whole point of this. I've showed you free body diagrams. Why are they so handy? Because they will allow us to solve force situations. We're going to use a tug-of-war analogy. We're going to draw a free body diagram, carefully labeling all the forces. And then we're going to use our knowledge of physics to figure out, to decide which force is the winning or the strongest force. We're then going to use the following equation. Here it is. Winner, takeaway, loser equals the net force, F net. Where F net is always equal to MA. In fact, I told you last day that force, that F equals MA, it's really F net equals MA. That right there will bail us out, Hayden, of everything this year, everything in Physics 12, and to be honest, I bet you everything in first-year university physics, unless they decide to go all calculus on you and give you a changing mass. Let's try this. Ready, Michael? I'm picking on you. So here's the picture. It says this. Suppose a box is resting on ice. Okay, I can imagine that. And the following forces are acting on it. Part A says, add any forces that you think are missing. Really, we're going to do a free body diagram. There's the box. What are the forces acting on it, Michael? Get the obvious one. I'm going to go straight to MG, if that's okay. Michael, does this question suggest that the box is sinking into the ice like quicksand? Does it suggest that it's flying into the air like Superman? So vertically, what's my net force vertically? 0. Which means if I have gravity pointing down, I have to have an arrow pointing up. How long will I draw that arrow? Bigger, smaller, or the same size as gravity? So for me, mine looks about like that. And that's going to be, gravity pushes down on the ice pushes back on gravity. You okay with that, Karn? And then, Michael, I'm just going to transfer the two from the picture. It looks like I have a 14 newtons going this way and a 6 newtons going that way. And you'll notice I even eyeballed it. I made the 6 a little less than half as long as the 14, because 7 would be half of 14. You okay with that? Okay. What does B want me to find? You're reading the wrong question. I know, that's why I said that. Otherwise, I wouldn't have. Okay. Right? 6 and 14? You okay with that, Karn? Okay. Here's it wants us to find an acceleration. I can't give you the equation that works all the time. I can give you the approach. Our approach is going to be winner, takeaway, loser equals F net. Michael, look at my diagram. Which force do you think is winning? Can you say definitely the 14 newtons? The bigger force. Takeaway. Which force is losing? And what did I say F net always equals? Yep. It's okay. By the way, eventually in your notes, you might skip this line, the winner minus loser, and you might go straight to this line, but we're going to put this in our notes as a reinforcement. Michael, what's this question asking me to find in part B? How will I get the A by itself? How do I know? What's the M doing to the A mathematically? So how will I get the A by itself? Divide. And in your head, without a calculator, what is 14 take away 6? So if I hear you correctly, what you're saying is, that's an 8. I'm going to divide by the mass, and if you don't mind, I'm going to put the acceleration on the left-hand side now. That's A? Yeah. 8 divided by 3. I'm pretty sure that's 2.6 repeating, yeah? That one I can do in my head. I'll go 2.67. 2.67 what, Michael? Acceleration. I can find an acceleration if I set up a good free body diagram, if I come up with a winner minus loser equation, and then I get the A by itself. But don't memorize this line. This line you will memorize just by using it. This is going to be our approach. Example 5. Example 5. Okay. Suppose this box is accelerating to the left at 3.2 meters per second squared. Okay. A says add any forces you think are missing. You know what? Really, what I'm going to do is a good free body diagram. Kyle, there's the forces. There's the box. What are the forces acting on it? Get the obvious one. mg down. Does this question suggest that this box is sinking into the ground like quicksand? Is it flying into the air like Superman? So there must be a force pointing up. How long? Exactly as big as gravity. Let's call it F ground. We will give that force a special name in a couple of days, but for now we'll just say that. What other force do I know? It's an acceleration, doesn't go in my diagram. I said force, not meters per second squared. What other force do I know? Which way? How big? You know a good abbreviation for the force from Billy? How about Kyle? I go F with a little b. Kyle, what other force do I know? Bigger, smaller, or the same size as Billy? How, and this is the key, how do I know bigger? There must be an unbalanced force that way. This is Newton's first law. I'll exaggerate it. Yep. Is that okay? And you can see Julie, and I have to go step by step, don't rush into this, and I will. You're going to be tempted, by the way, to stop drawing free body diagrams in the homework. I'm going to make you each time, first of all, Sage, I want you to get so good that it takes you about a second to draw them, which is not much time. In terms of time investment, Hayden, bang for your buck, a free body diagram is one of the best bang for your bucks that I can give you. Vertically, Kyle, what's my net force? 0, so I'm going to ignore it. Horizontal, oh, I've done part A. What does part B want me to find? You know what? I think what I'm going to do is this. Winner, take away loser, equals F net. Except, since I use blue in the diagram, and for me it's in color, I'm going to change colors, Mr. Duick. Winner minus loser equals Look at my free body diagram, Kyle. Who's winning? FA? Who's losing? FB? And what does Fnet always equal, Kyle? No. No. Michael, what does Fnet always equal? MA. Kyle, what does this question want me to find? Oh, how would I get FA by itself? What will I do with this minus FB? Well, really? So this is why I said I can't give you a one-size-fits-all equation that works all the time, but I can, Matteo, give you a method. And this is also why I snuck in the formula manipulation before Christmas, because I know you really can't do these without it. So you're saying plus the FB over? Is that what you're saying, Kyle? I agree with you. So you're telling me FA equals MA plus FB. Before I go further, I always pause and I do a quick variable check. Did they tell me M? Did they tell me A? Did they tell me FB? Well, now it's plug and chug. 5 times 3.2 plus 24. I should be able to do that in my head. Timesing by 5, that's the same as dividing by 2 times by 10. It's 16 plus 24. It's 40. Yes? Double check me. Psst. To times by 5, times by 10, divide by 2. 3.2 times 10, 32, divide by 2 is 16 plus 24. 40. Kyle, coming back to you. 40 what? It's a force. Yes. Right? Last one, and we're going to pause. Again, let me emphasize, Kayla, I can't give you a one-size-fits-all equation. I can give you a one-size-fits-all algorithm. Winner minus loser equals equals MA. Number 6 says, find the tension in the rope. In fact, this is the same picture that I put on the previous page. We have this mass accelerating up. Cassidy, what does this question want me to find? You know what? This is a job for a good free body diagram. There's the mass. You could put it right next to the, it doesn't matter, you can put the dot over here if you really wanted to, but somewhere it's worth drawing. What are the forces acting on this mass, Cassidy? Get the obvious one. mg down. I agree. Sorry? You're right. I think you were right. Okay, you know what? Let me walk you through it. Which way is this mass accelerating? Which way must there be an unbalanced force? Which way is this mass accelerating? Which way must there be an unbalanced force? Same question. Same answer. Okay, which way is this mass accelerating? Which way, therefore, must there be an unbalanced force? Up. So which way must there be a longer arrow than gravity? All of those are the same question, same answer. So you ready? Here we go. Which way is this mass accelerating? Which way, therefore, is there an unbalanced force? Which way, therefore, must there be a winning force with a longer arrow? There we go. That's the power of Newton's first law. If it's accelerating, there has to be an unbalanced force. Which force is that? It's the rope. What name did we give to the rope? What you were feeling right then until you got the right answer. Yes, tension. You okay with that so far? Oh, okay. What did this question want me to find? Let's write an equation. Now, my generic equation is winner take away loser equals Fnet. See my two forces in my free body diagram? Who's winning? Up. That's a direction. Which force is winning? Tension, like you're feeling right now. Yes! Minus. Who's losing? I agree. What does Fnet always equal? Careful. What does Fnet always equal? MA. That's really where F equals MA. Okay. By the way, also, I could have given you the tension. We could have found the acceleration, divide by M. So this works, but you have to draw a free body diagram to get the forces in the right places with the right plus or minus signs in front of them. What are we trying to find, Cassidy? How would I get the T by itself? Oh, good gosh, I like this. So if I hear you correctly, and I think I do, you're telling me it's going to be MA plus MG? Let's do a quick variable check. Did they tell me M? Did they tell me A? In the picture, did they tell me M? I already answered that. Do I know G? And I'll put a positive. I took care of the negative right there. There's where the negative 9.8 showed up when I pointed that arrow downwards. So I don't need to worry about that. It's going to be M 12 times 2 plus 12 times 9.8. I should be able to do that in my head. 12 times 9.8, that's going to be 12 times 10, 120. Take away 2.4. It's going to be 117.6 plus 24, 117.6, 137.6, 141.6. Double check me. I think I'm right. Yeah. 141.6? Am I right or no? Am I wrong? What, you thought plus means times?
No, I just missed the 12. Like, I did 12 times 2 plus 9.8.
It's not. It's 12 times 2 plus 12 times 9.8.
Yeah.
Which I think is 141.6, I'm pretty sure. I'll go to, you know what, Cassidy? I'll say 142 newtons. I'll go to 3 sig figs. Really, I should say 140, but whatever. I was proud that I got the decimal right, so I have to include that in my answer because, you know, yay, math. All we're going to do on Wednesday is practice a bunch more of these and what can we do with these. But for the remainder of class, let me pause the video.